So if you remember last time, or kind of what I guess last Friday, we talked about methods for solving numerical problems in 0D transient situations. Right? 0D transient means that we assume the entire body is at a single temperature. Now we're going to be talking about situations where the temperature is changing as a function of time, but there's also conduction happening within the body. Okay, so it's no longer 0D, it's 1D conduction. So just to start off on this, let's kind of come up with this conceptual model for how we think temperature changes as a function of time as it's conducting. So for this, let's take a kind of a sample problem, and we're going to say in this problem, so for time less than 0, our temperature is going to be at T initial. Okay, then at time greater than or equal to 0, our temperature is going to be at TS on the surface. So here, let me write some labels. So let's say down here, this is T initial at the bottom of the y-axis there. And I don't know, up here, let's call this TS. Okay, so we're at time equals 0. We're transitioning, say, immediately from an initial temperature up to some specified surface temperature. So in real life, what would this be? It might be something like you turn on a pump and all of a sudden there's a very large heat transfer coefficient at the surface, right? And you are pushing through temperature fluid at TS. And so effectively you're forcing that surface to be at TS. Okay, so then the question is, now we have this temperature, let's say this is a plane wall, right? And there's a temperature disturbance on that surface. How does that disturbance change as a function of time? Okay, so at time equals 0, right at the initial time step, when this happens, you might say, okay, well, we know that there's going to be a really steep gradient. So I'll try to draw this like this, right? So it's a really steep gradient. And this is like time at approximately 0, but just like slightly longer. So there's the entire temperature disturbance is really limited right to the wall. Right? Okay, so then as you go through time, you're going to start seeing this basically this wave of energy, or this temperature wave, start to propagate through due to conduction, right? So at time equals, let's say 1, you might see it start to look like something like this. So this is time equals 1. As you carry on, that wave just continues to grow, right? You see this wave continue to grow, something like this. Right? Time equals 2, and now working. Time equals 3, and so on. Right. So this thermal wave as a function of time is growing into the body. So we can talk about a few things in this. This length here. Let's draw this length down here. The length that the temperature wave has sort of penetrated into the surface, we're going to call that delta, lowercase delta t. Okay, so that's like the thermal wave depth. Okay, so I guess to come up with kind of an approximate model of how this temperature disturbance behaves as a function of time, let's go back to our toolkit for doing approximate understanding of models like this. So let's look back at a resistance model of this. Okay, and the goal is to come up with a relationship between, let's say, this delta T, the depth of thermal penetration, and time. Okay, so if we want to do that, let's kind of take, I need a different color here. So let's take this control volume here. Right, so whatever the width of this thermal wave is, let's make that our control volume for this surface. Let's come up with a model of conduction in this control volume. So if we look at this control volume, let's do an energy balance. It's going to be in minus out minus stored equals 0. We have no generation in this case. So let's look at what's going in and what's going out. So what's going out of this? Let's see here. So I'm saying here that there's heat going in, right? If you kind of think about what's happening here, we're adding heat into this, so there's this thermal wave that's propagating. Right, so we're adding heat into this. So we'll say there's a boundary condition sort of heat source coming in. There's nothing really going out, right? If you look over here at this boundary on the right-hand side, there's nothing going out. In fact, we could make it a little clearer. We could, instead of drawing our control volume right here at the edge, we could draw it slightly to the right. So we could just slightly move this over. Right, and here in this region, it's a little hard to see, but in this region here, dt dx is 0, so it's effectively adiabatic, right? It's a little hard the way I've drawn it, but there's no heat leaving, right? There's no place where heat is going, so there is no out. Okay, so we're just left with in and stored in this case. So let's come up with terms here. So what do we have? Going in, we have q dot conduction, which is approximately equal to T surface minus T initial times K times A over delta T, right? This is our resistance model. So what are we saying here? We're saying that conduction in this body is approximately the temperature Ts on the left side, okay, minus the temperature down here on the right side, times the resistance between those two things, right? And the resistance between those two things is scaled by that thermal depth, right? So kind of like effectively, we're approximately saying that this line here is linear, right? It's basically a linear profile or close to a linear profile. So we can model it like a plane wall resistance. Okay, again, we're doing this as an approximate model just to come up with some kind of useful parameters that we can use to describe the problem. Okay, so that's conduction. And then what do we have for stored? So for stored, we have U, the stored energy here. So let's think about what, for our control volume, what is U going to be? So we've taken the temperature going from T initial up to T surface, but not everywhere through the control volume. So if we again say that that temperature curve is approximately linear, then actually what we have for an internal energy change would be approximately Ts minus T initial divided by 2. Okay, so it's that temperature difference that we have divided by 2, half of the temperature difference, times delta T, times the area, times the density, times the specific heat. Okay, does everybody see where that came from? Right, we're saying we're kind of, on average, we've raised the temperature or the internal energy to be about half the distance between Ts and T infinity. Okay, so we have our two energy terms here. So let's put these together. So if we do that, we end up with Ts minus T initial divided by, or times K times A divided by delta T. And that's equal to, on the right-hand side, ddt of Ts minus T initial, so T initial, over 2 times delta T times area rho C. Okay. Now in this expression, Ts and T initial are constant values. Area is a constant value, so those can be canceled out. So let's get rid of this. And let's get rid of area. And then we end up with this expression. So we say 2 times K, so we bring stuff over to the left-hand side, 2 times K over rho C is equal to delta T times the derivative, ddt, of delta T. Oops, delta T. Right, everybody see how we got there? Okay, so what we have on the left-hand side, 2 times conductivity over density times specific heat. This is actually a really important parameter for 1D problems. Okay, and this is called thermal diffusivity. Thermal diffusivity is equal to K over rho C, and we'll call that alpha. All right, thermal diffusivity is has the term alpha. The units are what, meters squared per second on that? You do the calculation there. Okay, so thermal diffusivity is a property of the material, but it's a combined property, right? And it's saying if you have a really high thermal diffusivity, right, that means conductivity is high relative to density and specific heat. That means heat's going to travel really fast in that body compared to if it was a low thermal diffusivity. Okay. Okay, so we have thermal diffusivity. So let's carry through, and we kind of have this relationship we're starting to form between delta T, but we don't really have a time component in this yet. So what we want to do is let's take this expression we have written for delta T in terms of thermal diffusivity. I'm actually going to replace this here with 2 times alpha, right? 2 times alpha over here. So let's take that and let's integrate it with respect to time. Because we have a derivative on the right-hand side. We want to get rid of that. Okay, so let's integrate this from, let's say, 0 to, on the left-hand side, 0 to delta T. Okay, so we want to integrate the left-hand side with respect to the spatial domain. And then on the right-hand side, let's integrate this with respect to, well, I'm sorry, I did it backwards. So left-hand side from 0 to time. Okay, so left-hand side from 0 to sometime T. Right-hand side from 0 to delta T. And then ultimately, we need to find a relationship between this time and delta T. Okay, so hang with me here. We'll kind of see where this is going. All right, so we do this integral, and we end up with the following. 2 times alpha times T on the left-hand side is equal to delta T squared divided by 2. Okay, so just doing those integrals. So again, we wanted a relationship between time and this thermal penetration depth here. Okay, so now we can solve this for delta T. End up with delta T is equal to 2 times the square root alpha times T. Okay, so using our approximate resistance model, we've just come up with a relationship between the thermal wave penetration depth, delta T, and time. And so it happens to scale with the square root of time. Right? And if you think about that, it kind of makes sense, right? You have this initial kind of rapid growth of the thermal wave, and then as time goes on, the growth will start to slow down because any new energy you're adding on the left, on that left boundary, has to conduct all the way across that growing wave, and so you kind of get this decaying growth with increasing time. Okay, so this equation, you can actually use this quite a bit, right? This is it's like one of the time constants. It's one of the things you can really use to characterize a problem. And in fact, we can kind of rewrite this. So if we want to rewrite this as a time constant, let's do the following. So we're going to write this as a time constant. We're going to solve for T. So if we solve for T, then we end up with, we'll call this tau diff, or diffusive time constant. Tau diff is equal to just L squared over 4 alpha. Okay, so L squared. So let's say I have some body, some wall, and it's a length L, right? It's a width L. It's a thickness, like the one side of the wall to the other side of the wall. That length is L. Okay, so if that's L, then we can characterize the amount of time it's going to take for heat to diffuse across that wall as tau diff is this relationship, L squared over 4 alpha. All right. So combine that with recalling that, recall that our other time constant was tau LC, the lump capacitance, which is R surroundings times the specific heat of the object, right? So we have these 2 time constants. One of these now tells us, given some disturbance in temperature, this is how long it's going to take heat to go from one side to the other. The other one tells us, given a disturbance in temperature, this is how long the body is going to take to come to equilibrium with its surroundings. Right, so internal equilibrium for tau diff, external equilibrium for tau LC. Okay. So with these 2 time constants, the first thing you do for any transient problem should be to calculate these things and decide, what's the sort of order of magnitude, which of them are important.